All right, today we're talking about the unsung heroes of the industrial world. They're these tiny, invisible workers that are in pretty much everything: our food, our fuel, even our laundry. They are completely transforming industries from the inside out, and we're going to dive into the incredible power of enzymes.
So let's kick things off with a question. How can you get all of these things, cleaner clothes, clearer juice, greener fuel, but do it using less energy and fewer nasty chemicals? It sounds kind of like a have your cake and eat it too situation, right? But it turns out nature already figured out the answer.
And here it is, the hero of our story, the enzyme. The best way to think about it is as a tiny biological machine. It's a natural protein that's designed to find a very specific chemical reaction and just supercharge it. They are nature's own catalysts, and they work with a speed and precision that is just mind-boggling.
Okay, so we've got these natural powerhouses. The big question is, how exactly are we putting them to work? Let's get into it and see how enzymes are becoming the green champions of modern industry.
This slide shows the difference perfectly. It's the old way versus the new way. On the left, you've got traditional brute force chemistry. That often means tons of heat, a lot of pressure, maybe some toxic chemicals. It's messy and it wastes a ton of energy. But then on the right, you have the enzyme approach. They just do their work in plain old water at normal temperatures. And because they're so specific, you don't get a bunch of junk you don't want. The bottom line? They're cleaner, way more efficient, and totally biodegradable.
So let's get to know these tiny machines a little better. You know, not all enzymes are the same. Just like a good toolbox, you've got different tools for different jobs, and each one has its own specialty.
First up, we've got the molecular scissors. Their official name is hydrolases, but honestly, scissors is the perfect way to think about them. They use a molecule of water to snip big, complicated molecules into smaller, simpler pieces. These guys are the real MVPs, the workhorses of the enzyme world. They're in everything from our food to our laundry detergents.
Next up, meet the electron movers. These are called oxidoreductases. Their whole job is to manage the flow of electrons, moving them from one molecule to another. And why is that a big deal? Well, think about breaking down really stubborn pollution or bleaching fabrics for our clothes without using harsh chemicals. That's where these enzymes shine.
So where do we even get these things? Well, as you can see, they're pretty much everywhere. We can grow microorganisms to produce huge amounts of them, which is really cost-effective. We get them from plants, too. But the really cool ones, they come from something called extremophiles. These are organisms that live in insane conditions, like boiling hot springs. And the enzymes they make are super tough. And you know what? If we can't find the perfect enzyme in nature, we can now build custom ones in the lab. Each source has its pros and cons, which makes this whole field incredibly dynamic.
Okay, we've covered what they are and where they come from. Now for the really fun part. Let's go on a quick tour and see these enzymes out in the wild, doing their jobs in places you probably interact with every single day.
Just take a look at this. The sheer range here is amazing. We're talking about biofuels, wastewater treatment, pharmaceuticals, detergents. The list goes on and on. It just goes to show you, enzymes are this quiet, foundational technology that's improving, well, almost everything.
Let's start with something you definitely have in your house right now, your laundry detergent. Have you ever wondered how it actually gets those tough stains out, especially when you wash on cold?
Well, the secret is a little enzyme cocktail that's mixed right in. You've got proteases, which are like little Pac-Man for protein stains, like grass or blood. Then you have lipases that go after grease and oil, and amylases munch on carbohydrate stains. It's a specialized cleaning crew, and because they work so well, you can wash your clothes in cold water. And that, right there, saves a ton of energy.
Okay, from the laundry room, let's head over to the kitchen. We've actually been using enzymes in food for centuries, but with modern science, we've taken things to a completely different level.
For example, ever wonder why your apple juice is so perfectly clear and not all cloudy? You can thank an enzyme called pectinase for that. How does your bread get so fluffy and stay fresh longer? Yep, that's amylases. Of course, the classic example is rennet, which helps turn milk into cheese. And anyone who enjoys lactose-free milk or ice cream can thank the enzyme lactase. It's all about making our food better.
So this all sounds pretty perfect, doesn't it? But there's a catch. Natural enzymes can be, well, a little delicate. They aren't always tough enough for the rough and tumble world of industrial processing. So the challenge became, how do we toughen them up?
Yeah, this really hits the nail on the head. Think about it.
Factories often use high heat or potent solvents to get things done quickly and efficiently, but those exact conditions can completely destroy a normal enzyme. To make them truly useful on a huge scale, we had to figure out a way to make them much more robust.
And one of the most brilliant solutions is something called directed evolution. It's basically like playing evolution on fast forward, but in a lab. Scientists take an enzyme's genetic code, make millions of tiny, random changes to it, and then they test all those new versions to see which ones work better under tough conditions. It's survival of the fittest for enzymes.
And I'm not exaggerating when I say this was a total game changer. This idea of evolving enzymes in a test tube was so profound it actually won the Nobel Prize in Chemistry back in 2018. It completely changed what was possible in this field. Now, the other big solution is a little more direct. It's called immobilization. And the idea is actually pretty simple. If an enzyme is too fragile when it's just floating around, why not give it something stable to hold on to? Give it a home. And you can see how it works here. You can literally attach the enzymes to a solid surface or trap them inside a tiny porous bead. By anchoring them like this, they become way more stable and resistant to harsh conditions. And this is huge, it makes them reusable. You can use them over and over, which makes the whole process way more affordable. So, when you put all of this together, designing better enzymes through evolution and making them tougher through immobilization, where is all this leading? Well, it's pointing toward a future that is increasingly powered by biology itself.
And this is really the ultimate goal. Enzymes are becoming the key players in what's called a circular economy. They are the microscopic tools that let us take stuff we'd normally just throw away, like agricultural waste, and precisely break it down to create valuable things like biofuels or bioplastics. It's literally about turning trash into treasure.
So let's just end on this thought. Nature gave us the original design for these amazing little molecular machines. Science has now given us the tools to harness them, to customize them, and to make them even better. With that kind of power at our fingertips, you really have to ask yourself, what big problem are we going to solve next?